Hello everybody and welcome to our sixth and final video of Unit 2 on supervised learning. This video is going to cover model selection procedures. How do we actually decide what is the best model for our data and how do we find and pick that data? Once again, this is a presentation by EDU Onyx. So to start, we are just going to use a simple Boolean function example. So we're going to try to learn a Boolean function from a set of data endpoints, and this is going to help expose a couple of the different problems and concerns that we should have when trying to make a pick between different models. So here's our example scenario. We have a Boolean inputs and Boolean outputs, 0 or 1, yes or no. And for this particular example, we are going to have 2 input points. So, in general, just mathematically, there is 2 to the power of d possible ways to write d binary values. Since we have 2 values here, x1 and x2, there are going to be 4 possible ways to write these Boolean values, these Boolean inputs. And then the training set has at most 2 to the power of d examples. There are at most 4 examples for this particular problem. And then there are going to be 2 to the d possible Boolean functions of d inputs. So in this particular scenario, since we have 2 inputs, we are going to have 16 individual unique hypotheses, and any one of them could be correct. So the process of learning is going to be where we start with all the possible hypotheses, the 16 you have here, and as we see training examples, we're going to remove those hypotheses that are inconsistent with the training data. So let's say we had the example point 0, 0, the first one in our chart here, and its output is supposed to be equal to 1. Because of that, we can remove hypothesis 1, 2, 3, 4, 5, 6, 7, and 8. Actually, for each distinct training example, we can remove half of the hypotheses, namely those whose guesses are wrong. So, in the case of a Boolean function, like our particular example, to end up with a single hypothesis, we would need to see every single training example. If the training set we are given contains only a small subset of all possible instances, as it generally does, then that is, if we know that the output should be for only a small percentage of the cases, the solution is not going to be unique that we find. So this is actually a problem. The data by itself is not sufficient to find a hypothesis because we would have to see every individual possible point to find a unique solution. So this is the ill-posed problem, and this is actually a problem with classification problems and regression problems as well. It doesn't just apply to Boolean functions. In order to find a unique hypothesis, we would have to know every possible value. However, with inductive bias, we can get around this. So the data by itself is not sufficient, so we make extra assumptions. The set of assumptions we make to have learning possible is called the inductive bias of the learning algorithm. One way we introduce inductive bias is when we assume a hypothesis class. So in our previous videos in learning the class of a family car, there were infinitely many ways to separate the positive examples from the negative examples. However, in assuming the shape of a rectangle, we introduce inductive bias. So that assumption of a rectangle as separating the family class was an example of an inductive bias. In other scenarios, such as in linear regression, assuming a linear function is an inductive bias. And among all the lines, choosing the one that minimizes squared error is another inductive bias. So we introduce these assumptions because, once again, the data by itself is not sufficient to find a unique hypothesis. So learning is not possible without inductive bias, but choosing the right bias, choosing the right amount of inductive bias is going to be what we call model selection. Because the question really is, how do we choose the right bias? And what is that going to give us? This is model selection, which in other words is just choosing between the possible hypothesis classes. Then it's important to keep in mind that the aim of supervised learning is to predict new cases. So how well a model trained on the training set predicts the right output for new instances is called generalization, and this is what's important. In our model selection procedure, we have to keep in mind that we don't want to select a bias that gives us zero error on our training data but cannot predict new future cases. Instead, we want to choose the amount of bias that is going to give us the most accurate predictions on novel cases or new instances of data, because that is the goal of machine learning, is in supervised learning specifically, is to be able to predict these new cases. So how do we do that? Well, that's by comparing bias and variance. And so the error of bias is going to be an error from wrong assumptions in the learning algorithm. So for example, maybe we assume linearity when the underlying data isn't actually linear. And this is going to be an example of high bias because we apply a fairly strong assumption, such as the data is denoted by a line, and when in reality, the data could perhaps be the result of a polynomial. So this is going to give us underfitting. And underfitting occurs when a statistical model or machine learning algorithm cannot capture the underlying trend of the data. So we don't want to miss the trend of the data because that trend is what we're going to be using to predict future cases. So this is called underfitting, when our model isn't complex enough to find that actual trend. On the flip side, we have variance, and this is error from sensitivity to small fluctuations in the training set. So instead of mapping the underlying trend, here we are just making our model too complex and picking up on the noise and the small fluctuations instead of the undertrend. So an example would be using a higher order polynomial than necessary. Perhaps the data is linear and we try to map it with a polynomial. This is going to give us perfect accuracy on the training set. However, it's not going to be able to predict future data because we've missed that trend. So this is a result in overfitting. And overfitting occurs when a function is too closely fit to a limited set of data points. Remember, the problem is that we don't have every data point. We have a limited set here. So if we become too fit or too closely fit to this limited data set, we are going to miss the overall trend and not be able to predict future cases. So that is another problem. For best generalization, we should match the complexity of the hypothesis class with the complexity of the function underlying the data. So if our underlying data is following a cubic distribution, our hypothesis class should be a polynomial of order 2. Or if our underlying data is linear, then we should assume linearity. So this isn't always easy to know, and that is part of the model selection procedure, is comparing and contrasting some of these different hypothesis classes and seeing which one actually matches the complexity best. But we'll talk about that in a future slide. Here we have the bias variance trade-off. So this is just a great graphical representation of differing model complexity. So on the far left, we have high bias and low variance. We've made a bunch of assumptions about the data and we missed the overall trend. We are going to be not that great at predicting values in our training set, and also not that great in our test sample either. But on the far side, we're going to absolutely nail our training sample. We are going to have very low prediction error because we've made very little assumptions and we have high variance. Maybe we're using a very high order polynomial and it's capturing all those little fluctuations and the noise in the data. However, when we try to use that on the test sample, the red line here, we're once again going to get a high error. So the key is to find that middle point where we are matching the model complexity with the underlying data so that we can minimize the prediction error on our test sample instead of the training sample. So this brings us into the process of cross-validation. We are going to divide our data, the data that we have, into two parts for this process. The first part is going to be the training data. And we're going to use that to fit a hypothesis. And then on the flip side of that, we are going to have the validation set, which is going to be used to test the generalization ability of our hypothesis. So assuming a large enough training and validation set, the hypothesis that is the most accurate on the validation set is going to be the best one. Or it's going to be the one that has the best inductive bias. So we've made the correct amount of assumptions about the data. And this process of finding this best model is called cross-validation. So for example, to find the right order in polynomial regression, given a number of candidate polynomials of different orders, or polynomials of different orders correspond to different hypothesis classes, for each order, we find the coefficients on the training set, calculate their errors on the validation set, and then at the end, we would take the one that has the least validation error as the best polynomial. So not only are we optimizing our parameters, but we're also finding the best hypothesis class for our data. And that is why this validation set is very important. Because if we only use training data, the higher order polynomials or the more complex the algorithm is always going to have a lower error on the training data. But that's not necessarily what's important. It's the ability to generalize to new instances. So it's important to note that if we need to report the error to give an idea about the expected error of our best model that we just found in cross-validation, we should not use the validation error. We have used the validation set to choose the best model, and it has effectively become part of the training set. So because of that, we need a third set, and this third set is going to be a test set, or sometimes called the publication set. And it's going to contain examples not used in training or validation. And so maybe an analogy for that would be that in our own lives, when we are taking a course, the example problems that the instructor solves in class while teaching a subject form the training set, whereas exam questions are the validation set, and then ultimately it's the problems we solve in our later professional life that are the test set. So if you're needing to report error, you should probably divide the set into 3 parts. The training data to fit a hypothesis, the validation set to test generalization ability or test and make sure that we have picked the right hypothesis class, and then ultimately a test set to demonstrate the amount of error. So this is going to bring us to the end. We have our model once we've done this process. So these concepts are going to be reinforced when we go through our bonus Python project that's going to be included for this unit. So we're actually going to use a couple of different models to solve a multi-class classification problem, and we can compare and contrast the results on our training data and our validation data to see which one actually is the best. So hopefully this process of model selection will become more clear if you participate in that project. And I highly encourage that you do, because actual hands-on programming examples are going to be the best way to learn about supervised learning and machine learning in general. So I hope that you're back for that project, and thank you for listening to Unit 2 covering supervised learning. In Unit 3, we are going to cover unsupervised learning, and that's a whole other beast. And so we will dive into that soon. Thank you for listening.